what we started with, but it's been a week, so with stacks and queues, finishing out list data structures basically. It's been a week though, so I'd like to take a little bit of time at the front to remind ourselves of what we've covered so far as stacks and queues go. They're very simple once you are able to just simply visualize them. But their actual implementation can be complicated, and I'll show you why here in a second if you're naive about it. So remember that the whole reason that we want stacks and queues is because we want more structure. We call them data structures for a reason. We want more and more and more structure, and that's what you'll see as we look at more other data structures like trees, then binary search trees, then heaps. By adding more structure, we're adding basically we're making them more efficient for various operations. With respect to stacks and queues, they're restricted access data structures, meaning that they're efficient because we restrict how you can use them. Both of them have two basic operations that give you a structure as far as LIFO and FIFO. So remember that a stack data structure is the last one in is the first one out. It's a stack. It's like a stack of dishes. You don't want to take a dish out from the bottom or the middle or something. You take this. The first dish that you take off is the one at the top. You also don't want to be inserting them arbitrarily into the stack because then the dishes will fall over. Instead, you push the dish onto the top, right? So those two operations, push and pop, are the basic operations for a stack. And again, the visualization is here that you always push at the top, and so you build up this stack of dishes until you're done, or you want to push, then pop, then push, then pop. You want to go back and forth, whatever you want to do. But when you do start popping off the top, you only pop off the top. You're not allowed to pop something at the bottom because it's a restricted access data structure. If you want to be able to do arbitrary operations, you want to be able to insert anywhere, you want to be able to retrieve from anywhere or remove from anywhere, you're talking about a more general list data structure, which we've already covered. You can do it with a linked list or an array-based list, right? This one is a restricted access data structure to ensure that everything is efficient depending on how you want to use it. So once you've popped everything off, of course, you've got an empty stack. So what I wanted to do before we go on to queues here is I want to discuss briefly how we might implement this. So implementation. So ideas. How do you want to implement a stack? We need to, it's kind of a list because it stores stuff. It stores stuff in the order that you put them in. So maybe we could reuse something we've already covered. Maybe we can use a list, right? We're going to use a list, but we're going to restrict it so that you can only push and pop elements. So I've got a Eclipse open here, and I've already got a class called stack. And you'll note up here that I've imported something. Don't ignore those for now. So how are we going to implement this? I want my stack to own a list. Okay. A list of, for now, we'll just say integers. Integer. This is a stack only for integers. You can go ahead and use polymorphism, parameterized polymorphism, to make sure that this is a stack that can hold anything that you want. But for now, I'm just going to keep it simple. I'm going to say that it's a list of integers that you can put into the stack, like the visualization that I just ran. I'll call it L, or I'll just call it list. Right? Now, should I make this, like it is right now, package protected, or should I make it public, or what should I make this? It should be private, right? I don't want the outside world to arbitrarily access my list. I want to restrict access to it, so I'm going to make it private using encapsulation. Then I'm going to advertise to the outside world how you can use this stack by creating methods. Public methods using abstraction, public, void, push, right? And we'll push an integer, x, right? We'll come back and implement this in a second here. Public int, or integer, right? It returns an integer, pop, right? So if you call pop, we'll take whatever's on the top of the list, or top of the stack, and pop it back to you, right? Now, I've got, we'll just leave it like this for now. Now this is a list. Is there a top? Is there a bottom? No. So we need to designate a top or a bottom, right? Again, this is abstraction. Under the hood, using composition, I've got a list data structure that is implementing a stack, but then I advertise to the outside world that you can only push and you can only pop. So I need to designate which one is your top. Is the top the front of your list, or is the top the tail of your list? It doesn't really matter. I'll go ahead and go with this is my top over here. The beginning of the list is my top. So let's go ahead and implement this. I want to push an integer onto the top, meaning I want to insert it at the front of the list. So all I need to do is this.list.add at index 0 the element x. Right? So I'm always pushing on this end of the list. Push, 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 push. If you want to, take this list and put it vertically, and now this is clearly the top of your list. You're always pushing onto the top of it. Well, if I'm always pushing on the top of it, at index 0, then how should I pop off the top? Return, well, here, this.list.get the element at index 0, and I can return that. Except for, is that really a pop operation? That's here's the element at index 0 for you. Did I take it off? No. So I need something else. Is there something that will help me with this? This.list.remove element at index, and guess what it returns? You can't see it, it's very small here, but guess what happens when you remove it? It also returns it. So remove the element at index 0, and I can simply return that. Right? I'm being consistent about it. If you wanted to choose the other end, the tail, that's perfectly fine too. You just need to be consistent about it, that you're pushing and you're popping at the other end. Okay? Now this does have some implications here. First of all, let me go ahead and come down here and write some testing code. I need a stack, s is equal to new stack. Right? And I'll just go ahead and push on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for int I equals 0, I is less than 10, I plus plus. I will go ahead and say s.push, right? I. Right? So I'll push 1, push 2, push 3, all the way up to push 10. Great. And then I'll go ahead and pop all of those things. So let me go ahead and copy this. And instead, I'll go ahead and also print them at the same time. System.out.println s.pop. There we go. Now, obviously, this is still not going to work, but let me run it and see what happens. I'm going to get probably a null pointer exception. Why? What's null? Oh, this is actually a good news flash here. All right. Can you tell from that stack trace right there what's null? Nope, not from the stack trace. There's a JEP, I forget what JEP stands for, but there's a proposal for, it might make it into Java 13 in in 18 months or whatever their release dates are now, 6 months from now. There's a proposal to change the inner workings of Java so that it tells you, when you get a null pointer exception, it tells you exactly what variable was null when that exception occurred, which is a very nice thing to have. It should have been there from the beginning. The reason it was not in there from the beginning is likely because it's going to take, it's a performance hit. You actually have to keep, when something gets compiled, the symbols are not preserved, right? When you call an integer x is equal to 10, and then you want to print out that value through a debugger, x is lost. The variable name is lost because it's not preserved in the actual compiled code. You saw this last semester when we used GDB. You had to compile with GDB using the G flag. That preserved all those symbols so that the debugger could actually print out x has this value, right? It knew what x was because you compiled it with the G flag. So it's something that may be coming to Java soon, and it's very, very, very nice enhancement feature. But the only thing that can possibly be null here is my list. I never initialized it, did I? All right. So let's go ahead and create a constructor, public stack. Right. And I'll go ahead and initialize this list. I need a new. What kind of a list should we do? Well, let's be naive about it at first, and let's do an array list. Okay. And this is going to work, but that's only because I'm pushing 10 things, right? I pushed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that's the order that they get popped off in, right? 1 at the bottom, 10 at the top, so when I start popping, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That's exactly what I get here, right? Okay. Let's, I'm going to go ahead and get, well, here, I'll just comment this out and preserve it for when I post the code. System.out.println, done. Right? Let's bump this up. Let's not do 10 things. Let's do 1 million. There we go. So is 1 million a lot of things? If there were dollars, that'd be a lot of things, right? And not even in today's world, but is 1 million, is that a lot of things? No. Would you expect this to run quickly? Yeah, okay. Let's run it. The stop button is still there. It's still running. Right? It has not printed done yet. Right? 1 million things is nothing. But our naive implementation of this is because we didn't understand the data structure, right? We didn't understand how a list is implemented. Let me go ahead and stop this. We'll take some time here because I have to click stop 100 times now, apparently. There we go. All right, fine. Now it's finally stopped. Okay. Let's come back up here. And let's think about what I'm doing here. I've got an array list. Say that I was able to get to the point where I've got 500,000 things in there. Right? There's 500,000 things in there, and where do you want to push? You want to push it at the beginning. It's an array list, so it's being stored as an array. Is there enough room to put this thing at the front of the array? No. What do I have to do? I have to shift everything down, and now I've got room to put something in that array. Right? Occasionally, I will have to recopy that array like we did with our implementation. I'll have to recopy that array because once it's full, right, that array, then you can't change the size of an array, a static array that is. So you have, once it fills up with 100,000, I have to copy it over to something that's of capacity 200,000. So I'm copying that stuff over. That's not really that big of a deal. What's the big deal is if I've got 500,000 things in here and I need to insert it at the front, I have to shift 500,000 things down and then insert it. On the next iteration, I have to shift 500,001 things. I have to shift 500,002 things, 500,003 things, 500,004 things, right? Does that sound efficient? No. All right, let's go back to the drawing board. What kind of a list would you propose as maybe a better implementation for this idea? Maybe a linked list, right? And by the way, the array list and linked list, I'm using the Java built-in ones now. And let's go ahead and try this again, right? Would you expect it now to sit there and take seconds, minutes, days, weeks, years? Nope, it's done immediately. Why was it done immediately in this time? If I've got 500,000 things in a linked list, I'm pointing to the head, maybe I'm pointing to the tail, but if I'm inserting at this end, do I have to shift everything down? Nope. I create a new node, make that new node point to the old head, and update my head. I create a new node. I'm building this way. I'm not shifting everything down to make room for it. So if you're going to insert at the front like this, then a linked list is probably a better solution and probably a better implementation here. Right? But you only know that if you understand the underlying data structures and how they work. Again, one of the mantras of this course and one of the themes of this course is smart data structures and dumb code are a lot better than the other way around. But you have to understand smart data structures in order to use them properly. You've got this entire array of not literally an array, but you have this entire plethora of different data structures that you can pull off the shelf and use. Recognizing the correct data structure to use in the correct situation, that's what's really that's what's the most valuable thing that you can learn. Right? There's another quote that I use in CS3 from, I forget who it was, maybe Fowler, I'm not sure. If you want to become a great programmer, program every day of your life for the next 10 years. Or if you want to become a great programmer, you can program every day of your life for a year or two or whatever the quote is, and take a data structures and algorithms course. Because once you understand data structures and when you use them, when not to use them, then you make problem solving nothing more than taking off-the-shelf components, putting them together, writing some glue code, we call it, and now you've got a solution to the problem. Right? You didn't have to start from scratch anymore. So that's a pretty good implementation of a stack. Let me go ahead and add one more thing here. Some secondary functionality that you might like to put into it is maybe public int size, right? How many things are in my stack, right? Return this dot list dot. But now everything is in terms of the list that you have in your using composition, right? I'm not reinventing the wheel. Instead, I'm using the functionality that I already implemented in my list implementation. Or public Boolean is empty, right? And I can how would I determine whether or not the stack is empty? This dot list dot size, or I could just call this size. And when it's equal to 0, then it's empty, right? If it's equal to 0, then it's empty. If it's not equal to 0, then it's not empty. Right? And now I don't have to. Now I can come back here and I can put into a for loop here. While it's not empty, continue popping off the top until it is empty or something. You can also have other secondary functionality, very useful. Say an integer, a peek method. Right? What is peeking? Well, peeking is looking without touching. Right? You peek into the stack and you look and see what's on top. Return this dot list dot get the element at index 0. Note that I'm not removing it. I'm not popping it off the top and giving it to you. Instead, I'm looking at it and giving you what the value that's stored in the top there. Right? And even more valuable, how can I go ahead and change this so that it's not just integers? Instead, it's any type t that you want. I have to do what? I have to parameterize it, right? And this is no longer an integer. That's a type t, and everything else is perfectly fine now. Oh, except for this, I do need to parameterize this now without to not get that warning. There we go. Oh, there we go. Thank you. And probably return. There we go. The return type on pop. And then also this. Make everything generic. There we go. And now this stack is a stack without changing any of the other code, just making it all generic instead of integers. Now I've got a stack that can hold strings. I've got a stack that can hold doubles. I have a stack that can hold anything that you want. Right? I've also got secondary functionality here. Right? Now, I did not use my implementation of a linked list nor an array-based list to do this. So do you think I should also always should I use my stack implementation, or do you think that there might be something in Java that does it for me already? We'll talk about that at the end of the class today. All right. So use a list, right? But use it wisely, right? So for example, pushing and popping is very efficiently done using a linked list and adding, removing from the head. Right? Pushing and popping, by the way, can be done. It can be very efficient with an array-based list, but you need to be careful. How do you think? Does anybody have an idea? How could you use an array-based list? An array list to efficiently do everything. Something where you're not shifting everything down to make sure that you've got room enough at the front. Okay?
To keep track of what your end is and do it at the
Yeah, do it at the other end, right? If I've got 10 elements here, I need to keep track of how many things are in the array list, but the array list does that for me already. If I've got 10 things in here, I need to insert at index 10, the size. If this is my top, then I'm going to pop off that top. I take the thing at the end of the list and return that, right? So, i.e., using the other end, right? The tail. Right? I hesitate to call it tail because that implies that it's a linked list, right? Moreover, you can also have secondary functionality, right? For example, is empty. You can have get size or size, right? You can have what else did we do? Peak, right? Etc. You can also modify your stack to be a bounded stack. Right? Now, a bounded stack is simply something that has a maximum capacity. For example, if I come back here and I put not just a list, but I also have a private int max capacity, and maybe a default of say 10 here, then how would I modify these things? I would say instead of just pushing it, go ahead, push it as much as you want. I would check that capacity. If this dot size is at my current maximum capacity, then I can not do it, right? Else, yeah, go ahead and push it if there's still capacity there. What should I do here? If you've reached a maximum, if you want to have a maximum capacity, say at most 100 things can be in this stack, what happens when you push the 101st thing? What should you do? What's one thing that we could do? You could what? We could throw an exception. We could throw a new, I don't know, stack full exception, right? We could define our own exception and do something like that. Or since I don't want to define that right away, I'll just say an illegal state exception. Stack is full. Right? And now when I go down to do this for 1 million, I'm certainly going to get in trouble here with pushing the 11th thing because my default maximum was 10. I could, of course, take that in as a constructor. I could do that in many different ways, right? What's an alternative? It's a void function, right? How did we do this in C? Remember in C when we wanted to communicate an error, but we still wanted to return a value, right? We made it so that you had a pass-by-reference variable that's the return value, right? You want to get error distance between latitude, longitude A and latitude, longitude B. We took those four as inputs, but then we also took a variable by reference so that we could put the answer into that bucket, right? That opened up the return type, the return value here, because now it was void. We could use that as an integer to return an error flag. I could do the same thing here, since it's a void function. I could return a Boolean, right? That returns true or false, return now this one it's reached its capacity, so we're not going to put it on the top, so we'll go ahead and return false. Your operation had no effect. Right? It was false. It was not put on the top of the stack. Of course, under a successful operation, we should return true. Right? Both of those things might be something that you want. Right? In fact, you might want both of those things at the same time out of your data structure, or the option to do one or the other. Keep that in mind for the end today, right? But that is another thing that you can consider when you're implementing this stack. Should it be throwing an exception or return a flag value, right? True if successful, false if not, right? Etc. So all that is the secondary functionality that you can that you can get into, right? Let me check something really quick. But otherwise, you have all the same exact issues with the other data structure that we looked at. Let's go ahead and go over here. What was the other data structure that we looked at before the break? Stacks and queues, right? So actually, no, let me go ahead and just take this stack and copy it and paste it, but I'll call it a queue instead. And where is it? There we go. All right. Now, this is a queue. It still has a list. Maybe I'll go ahead and keep it a linked list for now. That's good enough. It has a maximum capacity if you want to do that. Should I be calling this a push, though, anymore? If you want to add something to a queue, what's it really called? I think we talked briefly about it. There are various things that you can call this. Java, for example, calls them offer and poll. Right? Why is it called poll? P-O-L-L, poll. If you've got a queue where people are waiting in line, right, and everybody's taking a number, right? And they might not actually be waiting in a physical line, but they're waiting in the room. Everybody's got the number, and then somebody their own number, and somebody says, "Now serving number 23." Right? Then they come up and they're the next ones to be served because they're the next. The first one to pull a ticket is the first one to be served. Right? That's why they call it polling. Who's next? Now serving number 23. You announce that you're polling the room to see whether or not they're still there or they left because there was too much waiting time, right? Offering is the opposite. I don't know why they call it offer, but offering is offering it up to the queue, inserting it into the queue. I like to use other words. I like to use enqueue, right? And if you enqueue something, then you could dequeue something, right? So if you're enqueuing something, well, you can check to see if you're already at your maximum capacity and either throw an exception or return false or whatever. And if you want to, this is a linked list, so inserting at the head at index 0, that's perfectly fine as well. But if we're going to insert at index 0, then where should we remove? Should we be removing from the same end? Here's your queue. You insert at index 0. Where should you remove? You enqueue at index 0. Where should you dequeue things? At the other end, right? So not at the front end, but at the end. Where is that? This dot list dot size. Is that correct? There are 5 things in there. Then the last one is at index 0, 1, 2, 3, 4. So -1. Right? And now I've got to change everything down here. NQ, Q. There we go. Maybe one of the reasons that they don't use NQ and DQ is because there are too many E's and too many U's. It gets really hard to do it, right? And let me go ahead and restore this now. And we'll go ahead, instead of popping, DQ, right? There we go. And let's go, maybe I should change the stack up here. Well, stack is full, queue is full. There we go. Otherwise, I think everything else is exactly the same, right? Let's go ahead and run this. There. If I insert it as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then the first one in, 1, was the first one to get dequeued. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So great. We've implemented both of these data structures using a linked list. Linked list, as long as you're keeping track of the head and the tail, both of those operations are going to be efficient. Right? So again, to review, let me go ahead and go with, I need to pull in, where's my queues? There we go. Right. So there are the notes from the queues from last time. There we go. Come on. There we go. We covered that last time, but again, the implementation, same. Use a list, right? And using composition ensures. Note that here, I could have used inheritance. That would have looked weird, though, right? First of all, I would have had to decide once and for all: is it going to be a linked list or is it going to be an array list, right? And that would have locked me into one or the other. If I was going to inherit from this one or going to inherit from this one, I can't inherit from both because that leads to the diamond problem. Remember? So maybe if I chose a linked list, all right, fine. I can inherit from that. I can make a stack and a queue and then override their functionality. Can I, though? Remember up here with the linked list, you've got arbitrary inserts, arbitrary deletes, arbitrary retrievals. Does that sound like a queue? No, a queue is a restricted access data structure. Is a queue a list? Not really. It uses a list in our implementation, but it doesn't follow that hierarchy. Right? I would still have insert at index I, right? And so you have your queue here, and then you could arbitrarily insert things into that queue. That doesn't sound right, right? That's a list, right? A list is not a queue. A queue is not a list. So instead, I chose to use composition over inheritance, which is in general actually the preferred approach. I'm using composition here because the queue owns a list, right? It is composed of a list inside the class, and that's how it gets everything done. But it does not implement a list data structure. Right? If I did this, then it would lock me into that hierarchy, and that, or implements, right? Or extends. Right? And you can't even do that because a list is an interface, whatever. It extends a linked list, right? That would probably be a very bad design because, again, it locks you into that hierarchy, okay? All right. So I'm using composition over inheritance, and I just make sure that insertion and retrieval or removal are done at different ends, right? And it doesn't matter which end, by the way. I think I even forget which one I just did. I inserted at the head. I removed from the tail. Well, you can go ahead and insert at the tail and remove from the head if you want to. It's just taking this list and flipping it around. There is no top. There is no bottom. There is no left. There is no right. It's just a bunch of electrons on a bunch of hardware, right? There's no orientation there whatsoever. The key is that to be efficient, your linked list needs to keep track of both the head and the tail, right? Otherwise, if you didn't have, like in our implementation, we only kept track of the head. If I wanted to insert at the head, that's going to be efficient. But if I've got a million things in here and I want to retrieve from the tail, and I'm not keeping track of the tail, then what do I have to do? I have to start at the head, traverse all the way down to the tail, traversing 1 million times until I get to the thing at the end, and then finally returning it. And that's why it's required that it's necessary for efficiency to keep track of both of those things if you're going to use a linked list for a queue implementation. Right? You can efficiently use a static array, or an array-based list to implement a stack, or a stack or a queue for that matter. Efficiently, just too many F's there. There we go. How might you do it, though? I want to insert at this end and retrieve from this end. Well, to insert at this end, we've still got that problem of shifting things down, right? I want to avoid that. So what I do is, instead of shifting it down, and this is all, the index 0 is always my head, and index size -1 is always my tail, I keep these floating around. That if I insert if I insert something at the head 0, well, 0 is now my head, and then if I insert 5 things, now my tail is index 4, right? If I'm removing something, that means I need to remove this. Well, I don't shift everything down. Instead, I just move my pointer over, right? And it's not really a pointer; it's just a number, right? It's an index indicating where the head is, right? If I insert something, I move this down. Insert, insert, insert. If I remove a DQ, I move this down, right? Now, eventually, you're going to get down to the end of the array. That's OK. What can you do now? Bring it back over to the other side. Right? Keep inserting, keep removing, keep inserting, keep removing, and just have these two floating numbers going all the way across. At some point, you might need to resize it. Right? If it's full somehow, then you might need to resize it just like an array-based list. But you can efficiently do it. It's just that it's a lot harder. There's a lot more to keep track of. There are a lot more failure points, so why even bother? Right? Just use a linked list, and you're fine. Right? All right, the secondary functionality would be the same. You could have, we already did. In fact, we didn't have to do anything to it. Right? Yeah. Peak is empty, size, the capacity constraint if you want to. It's all the same thing. But there are other variations of stacks and queues. Right? For example, you could allow arbitrary removal of elements, right? You could allow arbitrary removal, insert, or retrieval of elements, right? But why would you do that? If you're arbitrary, there we go. Why would you allow arbitrary removal, insertion, or retrieval of elements? What am I describing there? You can insert anywhere that you want. You can retrieve anything that you want. You can remove anything that you want. What is that? That's a list, right? you're shopping for the wrong thing then. If you need arbitrary access to your data structure, arbitrary access to your list, then you need to use a list. Only when you need a stack or a queue should you be shopping for a stack or a queue, right? But there are other variations that do make sense. For example, you could allow line jumpers, right? This is called a priority queue, right? Each element has an associated priority and is n-queued accordingly, right? So that things with high priority get to go to the front of the list. You could even you could have high priority, low priority, so just 2 levels of priority, or you could have, say, 20 levels of priority, where number 1 is the highest priority and gets to go to the front of the list. Number 20 is the lowest priority and always goes to the end of the list. 10 in between, well, he gets to jump ahead of all the 11s, 12s, 13s, all the way to 20s, but he doesn't get to jump ahead of all the 9s, 8s, all the way up to the 1s, right? So you can have an arbitrary number of priority levels. Now, of course, then you have to figure out how to break ties. If I've got 4 things at the head of the list, or head of the queue, that all have the same priority, say priority number 1, and then I insert something also with priority number 1, does he get to jump all the way to the head, or does he get to have to go to the back of the line? Or how do you break these ties when they all have the same priority? Generally, you just put it at the end. But a priority queue can allow something like this, right? Let's see. So, and then a dequeue operation always dequeues the element with the highest priority, right? And how would you implement this? We'll talk about that later, right? You could implement this, and you might even implement this in lab tomorrow, I forget. But you could implement this with just a simple linked list that also maintains a priority. And instead of inserting it, here's a queue, now here's the head of the line, here's the end of the line. Instead of simply just inserting it here, you check its priority. Well, does it have a higher priority than the tail element? If so, move ahead. Does it have a higher priority, higher priority, higher priority, higher priority? And then once you get to an element where, it should be inserted right there, right? That's kind of what a sorted list is, right? An idea for your last, the last phase of your project. But even that is inefficient, because if you've got an element with a very high priority and you start at this end, you potentially have to go all the way to the front of the array, right? It doesn't help to work from this end either, because if you've got an element with a very low priority and you start at this end, you eventually have to get all the way to the other end. Instead, there's a much better solution. Yeah. So if you wanted to do this with, say, something like this, if this were a priority queue, you'd have to keep an association of this element has this priority, this element has this priority. So I would change this so that the enqueue operation takes both the element and the priority. And then internally, I would store that in a map. Map this element to an integer indicating its priority. And that's how I would end up doing it. Otherwise, hint, there's already a hint in, when you get to the last phase of the project, to do something like this, you want to use a comparator, right? Not just numbers, but here's an element, here's an element. How do I tell if this one is higher than this one? I ask the comparator, right? Does this come before this one, or does this one come before this one, or do they have equal priority, right? And by asking the comparator, now you don't have to store numbers, you don't have to store anything other than the comparator itself, right? All right. Hopefully that was not that strong of a hint, but that's how you probably should do it in your last phase there, right? You also have something called a deck, right? And again, this is pronounced deck. It's spelled D-E-Q-U-E, so it's not a DQ. DQ would be D and then the full word Q. This is called a deck. A deck allows both insert and removal from both ends, right? That's where we get the name. It's a double-ended queue, so you can do it from both ends, okay? Why might you want to do this, right? here's an example of an application. Right? And before I write it down, let me ask you, go into Word, Microsoft Word. Right? You start typing, and then I don't like that sentence. I'll go ahead and erase that sentence. All right? I deleted one sentence. I need to correct that spelling over there. Okay, I need to delete that sentence right there. I've had now 3 operations. Oh, wait a second. That first operation, I screwed up. I should not have deleted that sentence. What do? Or what's another word? What do you undo? Undo this, undo this, undo this. And then, okay, well, now I need to go back and redo this. That's I can do that, though. Right? What was I keeping track of there? I was keeping track of operations. If I did A, I did B, I did C. If I undo, which one of these 3 things do I undo? The last one I did. The last one that the last operation that I did is the first one that I undo. Right? What does that sound like? A stack, right? So do operation, 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 undo, undo, undo. Right? There's a stack right there, keeping the order in which I did things. But now, do you think that Microsoft Word keeps an infinite, well, if you turn tracking on, yes. But do you think that Microsoft Word keeps an infinite record of everything that you've done with a document? If you say it's been open for an entire month, for some reason you've had your computer running for a month and the same document open for a month, and that you've been doing things constantly that entire time. Do you think there's enough memory to keep track of every single little operation that you've done for the last month? No. So we only keep a window, right? To keep it small, let's say that we only keep track of the last 5 operations that you've done. We can undo, 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 but now the stack is empty. Right? We can do operation, operation, operation. Now the stack is full. Do I keep these 5 elements if I do another one? No. What do? I put that on the top of the stack, but now if I've got a capacity of 5, I can't store 6 things anymore. What do I need to do? I get rid of, which one should I get rid of? Probably the oldest one. So this one drops off the face, and now I've got 4 plus the one I just did. Now I've got 5 again. I put things on top of the stack, but if it's a bounded capacity, the most logical thing for things to fall off the wayside is down here. I insert, I push, and I pop from one end, but also I can remove from the other end. Right? There's a perfect example of where you would want to use a deck to keep track of bounded number operations, so you can undo them. Right? And you need to work from both ends. You need a double-ended queue because you don't want to remove an arbitrary element. You want to remove the last element, the oldest operation that you've done. Another example is an LRU cache, right? Or a least recently used cache. Right? Not necessarily that you'd want to use a deck for this, but it's the same idea. You've got a cache. What is a cache? Or cache, if you want. What is a cache? What is a cache of weapons? It's a storage area, right? What is a cache in memory in a computer? It's a storage area where you can store values that you've computed. That's a cache, so that you don't have to recompute them every time. You just go to the cache and say, oh, I already computed that value. Let's pull that out. You might remember that we did something like this last semester when we showed how to get away from recursion, or how to avoid recursion using memoization, storing things into a cache so that you don't have to recompute the nth Fibonacci number. You just go to the cache and pull it out, right? But an LRU cache is you can't hold everything, right? Your cache is not infinite. Instead, once it's full, and you want to put something into the cache, you need to decide which one should I get rid of. Probably the one that was least recently used, right? You've got 5 elements in there and you want to put one in there. These first 4 have actually been used very recently, but this is the oldest one. So let's go ahead and get rid of it and replace it with the newest one. Right? And that's what an LRU cache can get you, right? It gives you a very easy way to keep track of elements with a very simple rule of only keeping the most recently used elements and getting rid of the least recently used elements. Right? There are a lot of other applications. Right? For example, with a stack. First of all, where have we seen stacks before? Where was the first place that you might have heard of a stack, say last semester? Function calls, the call stack, the program stack. Why do we use a stack for a program stack? Function A calls function B, calls C, calls D, calls E. Right? Now when you return from those calls, you want to it's maintaining an order, the order in which your functions were called, A, B, C, and D. Now, by simply using a pop operation to get rid of the one on the top, that means that you can return to the other stack frame, that you return to the calling directly to the calling function. Right? So you've got call stacks and programs in memory. And you can actually expand this and make this ever more abstract. What was I actually doing there? I was keeping track of function calls. If you have any application where you need to keep track of where you've been, for example, Hansel and Gretel. Hansel and Gretel, the fairy tale. It's not a fairy tale. Well, I guess there's a witch in it, so it has to be a fairy tale. The fairy tale of Hansel and Gretel, where the father can no longer feed them, or maybe it was the wife that didn't want to keep them. It depends on which version you're hearing. And so he leads them out into the forest, intending to abandon them to starve or whatever. Right? What did Hansel and Gretel do? They left breadcrumbs. Right, which were eventually eaten by birds, and that's how they got lost. But why did they leave breadcrumbs? Suppose that the birds didn't eat them. What were the breadcrumbs doing? They were keeping track of the path that they went throughout the forest. Right? In other words, just like the call stack, it was keeping track of all the function calls. Any application in which you have to keep, and we call this breadcrumbs, any application in which you need to keep track of breadcrumbs, you can use a stack, right? Because a stack does exactly that. You push onto the stack, and then you go LIFO order. That gets you back to the house so that you can go back to the very parents that tried to get rid of you, right? But no, anything that you need a breadcrumb. Breadcrumbs are all over the place in computer science. We use them in graph algorithms. Right? A depth first search of a graph, which you'll eventually get to, maybe in CS3 or something. You use a stack to keep track of. A graph is nothing more than a bunch of nodes, and then you go to the next node, go to the next node, go to the next node. To keep track of the path that you've walked in that graph, just like Hansel and Gretel, you've kept track of all the breadcrumbs in a stack, so that if you need to return to the origin, you can go in the reverse order, the LIFO order. Right? Unfolding, folding, recursion. Right? Why? How? If you want to avoid recursion, something that you'll look at in what I think your lab next week. One way that you can do this, I don't know if we do it in lab, I forget. One way you can do that is unfolding the recursion. A recursion is nothing more than a function call, function call, function call, function call. To get rid of all of that, you can simulate those function calls using a stack. And that's something that we'll do when we revisit searching and sorting in the context of algorithm analysis. For example, quicksort that we looked at last semester. Instead of doing the recursion, you simulate the recursion using a stack, right? Because a stack does exactly what a program call does, right? You can also use compilers. Use it for evaluating and compiling programs. Right? Actually, you'll do that this in lab tomorrow. There's something called pre-order or prefix notation. So if I want to multiply two numbers, 5 times 10, the normal way that we humans look at that is 5, then either asterisk or a cross or a dot or whatever you want to use as your symbol, 5 times 10, right? That's infix notation because we've got an operator, operand, and an operator. Well, for a computer, that's not really all that efficient. So instead, what's more efficient for a computer is to use what's called prefix notation. 5, 10, multiplication. Why is that more efficient? Because what you can do is if you see an operator, 5, you push it into a stack. See another operator, 10, you push it onto a stack. Now you see operand. Now you see an operator, multiplication. Right? what you need to do is then you pop off the two things that were on top of the stack, multiply them together, and then push the result into the stack. Even I'm too young to remember this, but has anybody ever seen anybody really old school using an HP calculator and going super, super fast on it? Why? In what context? Maybe an engineer?
Yeah, he was doing like calculating numbers at a store.
Okay. So some sort of an accountant going super fast. Was it an HP calculator? Definitely. Why? Because HP calculators support prefix notation, where you can do that. You just have value enter, and then multiplication, and then it puts it back into the stack so that you can go ahead and another value, multiply, and it's super, super fast. If you can get used to that. And that's prefix notation, which you'll explore tomorrow in lab. So that's another application, and it's used by compilers all over the place. With queues, you also, let me go with queues. Right. You also have many applications with queues, keeping track of processes or requests that come in a certain order. For example, a web server. A web server, you have many different people trying to access the web server. Requests come in. Well, you can't handle them all at once, but you still want to handle them. What you do is you can put them into a queue, the order in which they're requested, and then you have different threads that say, okay, I'm ready to handle the next request, and it takes care of it. This goes into something called the producer-consumer pattern, where you've got a bunch of producers producing requests, a bunch of consumers consuming those requests and sending back responses, and the way that you keep track of it all is through a queue. The first request to come in is the first one that gets serviced. Or you can go with a priority queue. An operating system. An operating system has many different processes that run on it. With Unix, you have something called a niceness property. And that's what I was alluding to earlier, where you've got these 1 through 20 priorities. You can actually run a program on Unix and set the niceness of it. I'll be nice about it. It's not a very important process. I'll go ahead and set the niceness level to 20, meaning that if there's another process on the system that needs that somebody wasn't so nice that they really need that process to run right now, they set their niceness to 1. Yeah, they have higher priority. Go ahead and let them do it. Right? Then the operating system keeps all those processes in a queue and decides which one gets to run next, right? Because not everything can run at once. Even if you've got multiple cores, you've got 4 cores with hyperthreading, you can run 8 processes at the same time. But if you've got 50 processes running at the same time, you can only run at most 8 at any one point in time. So the rest of them have to wait. They're waiting where? In a queue to be executed. And that's there's a priority queue that you can have line jumpers that have a higher priority. The highest priority, of course, are going to be the operating system processes themselves. They're the ultimate line jumpers. They can actually go into the front or something, right? But keeping track of processes. What else? So think about YouTube. When you hit play, or when you go and start watching a video, what happens? Does it give you the entire video at once? And then, okay, you have to wait for the download. Once the entire video is downloaded, all 50 minutes of that video is downloaded, now you can start playing. Do you have to wait that long? No, why? What does it do? Here's the play button, right? It loads a little bit. Now you can start playing, right? And as you're playing, as you're going through the video, okay, it loads up a little bit more. It loads up a little bit more. It loads up a little bit more. Maybe it drops off the old stuff. YouTube doesn't do this, but I think that they did it at one point. That the old stuff dropped off. But it used to be that it just loaded it all up automatically. Now they wait for you to get to a certain point, and then it loads up the next segment. What is this thing right here, other than the play button, the progress bar or whatever? It's storing data, right? How is it storing data? In what order is it storing data? Do you play the last 3 minutes first? Or do you play the first minute first? Right? The first one to get loaded is the first one to be consumed. What is this? It's a queue, but what's another name for it? If you're loading up data and then consuming data at the other end, that's called a buffer. Right? Buffers use queues to hold and then consume data. Right? And so you can use a queue for that. Right? Of course, consuming may or may not remove it. Right? Like if it's a YouTube video, just consuming that data, watching the first minute of video doesn't get rid of that data, but you consume it in the order in which you receive it. That's the same basic idea. And you store stuff into a buffer so that as you're receiving, you don't have to receive all the data at once in order to start processing it. If you did, then that would be very, very inefficient. Right? Lots of other applications as well. For example, graph algorithms. Another way that you can do things is breadth first search. Right? And this one you use a queue. So the difference between a depth first search, breadth first search, that's all graph theory that you'll get to eventually in, say, CS3 or something. Maybe you're doing it in 235 right now, or will be doing it. I don't know. But there are two ways of searching an area, right? You can, or let's just consider a maze, right? If you have a maze and you need to search it, you can go as deep as you want into a maze, and then when you hit a dead end, then you backtrack until you come back to the last turn of the maze, and then you go down that path looking for the way out of the maze. Right? That's a depth first search. You go as deep into the maze as you can until you to find the exit, and then only turning back once you hit a dead end. Another way that you can search a maze is what? If you're searching for a missing person, do they just go off? You go search over that 100 miles that direction, right? Is it likely that they're 100 miles away, or is it more likely that they're probably close about? So you search a perimeter. You search the area within, say, 500 feet. Then you expand that perimeter. You search an area within a half a mile. Expand that area, and you search an area within a mile. And then you keep expanding it until you find the person, or you've expanded it enough that you can go no further. That's called a breadth first search. You look at close areas first. And the way that you can achieve that very, very simply is with a queue. All you need to do is put stuff in and take stuff out. Dumb code, smart data structure. Right? And you'll eventually get to that. Okay? Otherwise, any questions so far? No? Okay. Let me see if I've got anything else. I think, of course, to cap it all off. Let's go with, let me open a web browser here. So again, to cap it all off, do you want to actually implement and use your own stack and queue data structures all the time? Probably not. Instead, if you're using this in Java, then my recommendation is to use a deck. Let me go ahead and pull it up here and bring it over here. Excuse me. All right. A deck has everything that you will absolutely ever need. Right? Well, as far as stacks and queues are concerned. A deck, you can work from both ends. So as long as you're consistent about it and always inserting at this end and removing from this end, you've got yourself a stack. As long as you're consistent about it and always inserting at this end and removing from this end, then you've got yourself a queue. If you want to do both, then you've got yourself a deck. In a way, a deck is more general than a stack and a queue. It is an interface, so you need to decide, well, what kind of deck do you want? Do you want an array-based deck, or do you want a linked list-based deck? And a linked list is a deck. These other two are ways that you can have a bounded deck, so you can set up a capacity of at most 1,000, and one of these, I think a linked blocking deck allows you to set a capacity, and concurrent linked deck has no capacity, but both of these are thread-safe versions of them. So if you've got multiple threads, you want to do this consumer-producer pattern, then you would use one or the other things like this. Right? Let's take a look. Hey, do you remember how I said maybe it would be nice if it threw an exception, if it was full, or an invalid operation? Maybe it would be nice if it returned a value, true or false, instead, so that you could say, I want to insert something, well, it's full. Okay, false, it had no effect. You get all of that here. Right? So if you want to insert at the first element, that is the head. And if you want to insert, then you use add first if you want it to throw an exception. If you want it to return a special value instead, you would say offer first. If you want to remove, remove first. That also throws an exception. Pull first returns instead a special value. Examine is the same thing as peek. If you want to peek, get the first. If you want it to throw an exception, if there is no first. Otherwise, if you want to return a special value, I believe the special value in that case is null, then you peek first. And it also doesn't allow nulls to be inserted into it. If you want to work from the tail, then there's add last, offer last, remove last, pull last, get last, and peek last. And because each one of these things is either an array-based stack or a linked list, it also supports all those arbitrary things that you can. Where is it? I thought it allowed you to. Oh yeah, it allows an arbitrary removal. Where's add? I think that there's offer. Nope, that's add first. There. An arbitrary add element to the queue represented by this deck. In other words, at the tail of this deck. So it looks like it does not offer arbitrary removal at all, but since you could probably get that in the actual implementations. But very nice. It's got all these things already for you: size, remove last, et cetera, et cetera. Right? Oh, and then methods inherited. Where is the method? Okay, nope, just from collection. You can you clear it out and remove everything. You can get, of course, the hash code equals, et cetera, et cetera. So if you ever need a stack or a queue, your solution is a deck. And then just use it as a stack or use it as a queue or use it however you want. You can work from both ends because it's a deck. Right. Any questions? Then I've already given you a preview of what we're going to be doing next. The preview was, let me go back to a stack here, and let's change this to an array list. Array list. All right. And we're still inserting a million elements here. Oops, it's done. Oh, that's because it's always, because it's at the maximum capacity. Let's go ahead and get rid of this for a second. There we go. And now I'll run this. I'll restore that when I post the notes. There. All right, this is running. Can anybody predict how long this will actually take if I let this run? Anybody? Just a ballpark figure. Is it going to take a few minutes, a few days, a few hours, or a few hours? I don't know. Let me go ahead and go to, oops, that's not what I want. Let's go to Wolfram Alpha. And what I want to do is 1 million times, just go 1 million divided by 2. All right. That's actually a rough estimate of the number of operations that I'm actually going to perform. All right. It's order n squared. What that means is what we're going to be getting into next. And let's suppose that my computer here, let's see if it's still running. It is. Let's suppose that my computer here is able to do 1 million operations per second. That's probably actually an overestimate. So it's actually going to take this many seconds, 500,000 seconds. 500,000 seconds to, I don't know, days? 5.78 days, all right? So if I let this run, and that's probably an underestimate because I overestimated the power of my computer doing 1 million operations per second. If I change this and I said, well, let's be more conservative, say that it's only 100,000 operations per second, that gives me 5 million seconds. That gives me 5 million seconds to days. That's actually now 2 months, all right? So understanding all that and being able to come up with those ballpark figures and understanding the growth rate, that if I go instead from 1 million, let me go ahead. That's actually done. Okay, the 1 million must have been an underestimate then. I can go ahead and, however many seconds that was, maybe that was 2 minutes. I'll go up to 10 million now. Let's suppose that took 2 minutes. Now estimate. Now I've got a good estimate in my head of how fast my computer is here. I've increased the size of my operations by 10-fold. And if it took 2 minutes before, how many minutes will it take now? 20 minutes? So 10 times as big? It's actually going to be about 200 minutes, so about 3 hours now instead. And that's because the growth rate of the algorithm that I'm running here is quadratic. Understanding that is where we're going to go next for Thursday and probably all of next week. Right? We're going to be looking at algorithms and algorithm analysis from a more rigorous point of view, rather than just running this stuff empirically and seeing, oh wow, this really sucks, this is taking forever, and wondering how long is it going to take for this to actually execute. We can come up with reliable estimates on how long it would take to compute this, and then make the decision of go ahead and hit that button and wait, or look for another algorithm. Look for a better algorithm that has better performance and better efficiency. Right? I'm not going to let it sit here for 3 hours to prove me right. I'm just going to give you a rough estimate. That's actually probably going to take maybe more. So 2 hours divided by 2. It might be just a little bit over an hour, but I'm not going to sit here and wait for it though. Right? All right. Understanding all of that starting Thursday.